What I want to show you is that it is the cosmic rays themselves which are affecting the climate. And I'm not going to show you all the evidence and get into all the technical details because we have Professor Svensmark here to explain a lot of that. But what I do want to talk about is what is the implications of this link, the fact that we know that the sun is affecting the climate and the fact that we know that it's through the cosmic rays. What does it imply to our understanding of 20th century climate change and 21st century temperature change as well? Okay, so what do I want to talk about? First, I want to talk about something which is not directly related to cosmic rays. I want to talk about climate sensitivity. And I'll show you, I hope, or I'll try to convince you, well, actually it's an easy audience to convince, that it's close to that of a black body Earth, namely that you don't have any large net feedbacks as the Ipcc advocates. And then I want to explain to you why it's important if you want to understand what's the meaning of the sun. What does it affect the climate? In order to answer this question, we have to understand how it relates to climate sensitivity. And I'll try to convince you that the sun has a large effect on climate. And of course, I'll want to dwell a lot on the fact that this link is through modulation of the cosmic ray flux and changes in the atmospheric ionization. Of course, the first 2 points are important if you want to understand what's going to take place in the 21st century. Okay, so what's climate sensitivity? Climate sensitivity is generally defined as how much the Earth's temperature, the climate system, will change if you induce a given change in the energy budget. The way that climatologists usually calculate it is they take a numerical experiment, they change the energy balance of the experiment. For example, a standard way to do that is to say increase the amount of carbon dioxide in the atmosphere by, say, 1% a year. But again, it says, Professor Weiser said, it's not changing the CO2 itself, it's changing the energy budget as if you have changed the CO2. And then you increase it for so many years. After you reach a double amount of the CO2, you let the climate system stabilize, and you ask the question, by how much is the temperature going to increase when you double this amount of CO2, or equivalently change the energy budget, in this case, by 3.8 watts square meter. And the climate sensitivity is basically the ratio between how much the response of the climate in terms of temperature change compared to the change in the energy budget that you induce on it, okay? This is the trillion-dollar question. What is Earth's climate sensitivity? Because if you knew what is Earth's climate sensitivity, you would be able, or you will be in a position to predict what will take place in the 21st century under a given emission scenario. Suppose you know by how much the CO2 changes, you will be able to predict by how much the temperature is going to increase. Now, the canonical values advocated by the Ipcc, if you open the Ipcc report, are somewhere between 1.5 to 4.5 degree increase if you double the amount of CO2. This large uncertainty is because you don't know with climate models what the different feedbacks are. And in fact, you can show that the largest feedback in the climate models, the difference in sensitivity that you get in one model compared to the other one, is in the recipe with which clouds are described inside the models. One model with one recipe for the cloud cover will give you a low sensitivity, and another recipe with a large, another recipe for the cloud cover will give you a large uncertainty. And since you don't know how the cloud cover changes for given changes in the temperature or amount of water in the atmosphere, basically the climate models cannot give you a reliable prediction for what the climate sensitivity is. Now, if you open the last Ipcc report, this number, 1.5, the lower limit of 1.5, changed to 2, but there's no real reason to think that it's now a little bit better determined. Okay, now, why is the question of climate sensitivity relevant, or how is it related to the question of whether the sun is affecting the climate? If we want to understand what happened over the 20th century, the standard picture is that you have the anthropogenic forcing, or primarily the anthropogenic forcing, and you see some kind of a temperature increase over the 20th century. Now, if you want to explain the temperature increase over the 20th century with the given anthropogenic forcing, you need a high climate sensitivity to do that. You have a given forcing. To get the large temperature increase, you need a high climate sensitivity. If you have a high climate sensitivity, you will necessarily predict that the temperature increase over the 21st century is going to be large as well. Now, if, on the other hand, there is another player in this game, namely that part of the warming over the 20th century is because of the sun, then it means that the net change in the radiative forcing induced over the 20th century is going to be larger. You're going to have the human contribution, and you're going to have the natural contribution, that of the sun. Now, if you have a larger change in the energy budget, then in order to explain the same temperature increase over the 20th century, you now need a lower climate sensitivity. Okay? You have a larger number times now a smaller number to get the same number, which is the temperature increase over the 20th century. This means that if you have a low climate sensitivity for a given emission scenario over the 21st century, you're going to predict a lower temperature increase, a smaller temperature increase. Okay, so the question of whether the sun is affecting the climate is very important if you want to understand what happens over the 20th century, and of course, if we want to understand climate sensitivity and predict what will happen in the 21st century. Okay, so the sun affects the climate. Here I'm very happy that Professor Weiser talked before me because some of the evidence he has shown you, so it's going to take me less time to cover this part. First of all, we have to realize that the sun is a variable star. It changes its activity over different timescales. It has variations on timescales of days. It has variations on the 11-year solar cycle, which is the largest variation. But over longer timescales, it has variations which are not quasi-periodic as you have in the 11 years, and are not eruptive as you have on the timescales of days. You have long-term secular variations in the solar activity. Now, the solar activity manifests itself in different things. For example, different amount of UV, the strength and configuration of the magnetic field, the strength of the solar winds, and a lot of other things change together with the solar activity. Ultimately, they all come about because the outer layer of the sun, the outer 40% of the layer of the sun, are what's called convective. When you boil soup, you see the same behavior. This advection of energy outwards from the center of the sun, coupled to the fact that the sun is differentially rotating, the fact that the equator is rotating faster than the poles, twist and amplify the magnetic field, and this is essentially what drives the whole solar cycle. And this thing, because you have a lot of chaotic behavior, you cannot actually predict what the solar cycle is going to behave, whether it's going to be stronger or weaker. But you have this 11-year solar cycle where the magnetic field of the sun flips, and you have also these long-term variations, which are very important because they're going to be, we're going to see them in this talk. Okay, over the different timescales, we see correlations between solar activity and climate. This is one of the first such publications in, say, more modern times. You see here basically a correlation between, in this case, the severity of winters in Europe and solar activity as mimicked by carbon-14, which, as Professor Weiser showed us, is proxy of solar activity. There is the famous relation between solar proxy and oxygen 18 to oxygen 16 isotope ratio in stalagmites in a cave in Oman. I think we've seen that. We've seen this graph as well, which shows us that when the sun is more active or less active, and it can be determined by, again, carbon-14, the amount of carbon-14 formed in the atmosphere. It correlates with the amount of ice-rafted debris that you see here in black. And you have many such examples. We've seen some in the previous talk. So over long time scales, we see that activity in the sun correlates with climate on Earth. We can look at what happens over the 11-year solar cycle, and we see that even on also on the 11-year solar cycle, there is a link between the solar activity and the temperature on Earth, or other climate proxies. Here you see two such examples. You see that together with the solar cycle, the sea surface, or the average sea surface temperature, changes with it. Here, this is something else. You can take the global temperature over the past 200 years and just fold it over the solar cycle. And when you do that, you see that there is a clear signal of about 0.1 degree change in the global temperature between solar minimum and solar maximum. Now, 0.1 degree sounds like a very small amount. But in fact, over the 11-year solar cycle, because of the large heat capacity of Earth, this 0.1 degree actually corresponds to a very large effect on the climate, as we'll soon see. OK, so we know that the sun has a very large effect on the climate. What I want to convince you now is that the sun has a very large effect on the climate, and it does so through modulation of the cosmic ray flux. So how can we do that? OK, so first, what's the picture? The sun affects the climate. The sun through the following. The sun changes its solar activity. The sun has a solar activity which changes. One of the things which changes is the solar wind. It's a tenuous wind of matter and magnetic field that the sun emits all the time. This thing modulates the galactic cosmic ray flux. Galactic cosmic rays are high-energy particles which come from outside the solar system. They actually come from supernova remnants. These are massive stars. When they die, they explode, and this explosion accelerates particles to high energies, and these particles diffuse in the galaxy, and they eventually reach the solar system. What's interesting is that, the solar wind modulates this flux of cosmic rays. When the sun is more active, then less of these cosmic rays can affect the climate, and can reach the Earth. And then the second thing is that the galactic cosmic rays, because they come at a high enough energy, they can actually penetrate the Earth's magnetic field, and they can penetrate the Earth's atmosphere. And in fact, the secondaries, particles which they produce along the way, can reach all the way down to the bottom of the atmosphere. And in fact, the major source of atmospheric ionization is cosmic rays. Here in this room, it might be from radon gas coming from the concrete, but outside, it's cosmic rays. Now, it was speculated already in 1951 that if there is, 59, that if there is anything in the climate which is going to be sensitive to the amount of ionization, it would mean that you will get a link between solar activity through the atmospheric ionization to the climate. And as we know from Henrik Svensmark sitting here, there is such a thing, and that's cloud cover. OK, as we'll see in the next talk, the cloud cover clearly varies together with the solar cycle. So how can we prove that the cosmic rays are those things that are the link that affect the climate, and it's not just a proxy of what the sun is doing? One way would be to look for intrinsic cosmic ray flux variations which are not associated with the solar wind. Suppose the cosmic rays that we get from the galaxy change with time. Then if cosmic rays affect the climate, then we should see a climate signature associated with this intrinsic variation in the cosmic ray flux. And the answer is that we do have such a link, which is not related to the sun. We actually have a few links. This is actually how I entered this field. I looked on very long timescales. Now, on very long timescales, what happens is that our galactic environment changes. Now, why does it change? The galaxy, the Milky Way, is a spiral-armed galaxy. It means that there are density waves which are propagating around the galaxy. And the interesting thing about these density waves is that every time a wave passes, it induces new star formation. And the massive stars that die and as supernovae and produce the cosmic rays, they actually live a very short life. So it means that most of the cosmic rays in the galaxy are produced right after a spiral arm passes. What does it mean? It means that as we roam around the galaxy, every time we pass through a spiral arm of a galaxy, of the Milky Way, we are going to witness more cosmic rays, and this should affect the climate. It should cool the climate because there's supposed to be more cloud cover. When you look at this movie, you will see, well, first of all, the Milky Way has 4 spiral arms that are radius, not 2. But the interesting thing that you see in this movie is that the spiral arms are waves which are propagating at one speed, but the stars which are composing them are propagating at another speed. So we're actually passing to the spiral arms every so often. How often? Well, the astronomical data tells us that we should pass spiral arms around every 125 plus or minus 25 million years. Okay, so do you see that in the climate record? The answer is yes. You can, first of all, you don't have to rely on astronomical data to determine what is the periodicity with which we pass through spiral arms and what should be the variations in the cosmic ray flux. What we can actually do, we can reconstruct what the cosmic rays have been doing by using iron meteorites. Iron meteorites live a long life in the solar system, and when they break off their parent body, their surfaces are exposed to the cosmic rays, and they actually record the history of the cosmic rays reaching the solar system. So we can use many meteorites to reconstruct what the cosmic ray flux has been doing. And when you do that, you see that the cosmic ray flux is varying in sync with the temperature that you see on Earth, temperature which was reconstructed using, by Professor Weiser's group. So you see that on very long timescales, the cosmic ray flux induce a large variations in the climate on Earth. Okay, you can actually look on longer timescales, and on longer timescales, you can reconstruct the cosmic ray flux. You can do that up to about 1 billion years. Beyond that, you don't have meteorites, and you see that it correlates. Well, it's a little bit technical. I won't get into it, but the thing is that you can use. You can see that there were about 7 oscillations in the cosmic ray flux over the past 1 billion years, and they synchronize together with the with the cold periods on Earth. Okay, another independent confirmation that cosmic rays are affecting the climate and not something else which is more directly related to solar activity is if we look at Forbush decreases. Here you have independent variations in the cosmic ray flux which are not associated with other solar activity. And you see that when you have this reduction in the cosmic ray flux over timescales of days, you get, following that, changes in the aerosols in the atmosphere and then in the cloud properties. There are, of course, lab experiments. This is the experiment that Henrik is going to discuss in the next talk, showing us that when there's more ions, we form more condensation nuclei. This experiment was repeated in CERN. We have the cloud experiment in CERN, and they see the same thing, namely that when you increase the number of ions in the chamber, you increase the formation of condensation nuclei. So you have here the microphysics of how the ionization affects the cloud cover. Okay, so we know that the sun affects the climate. We have seen that there is good evidence to suggest that it is the cosmic rays which are linking between solar activity and climate. The next question to address is how large is this link quantitatively, and what does it imply to our understanding of 20th century global warming? Okay, so we can estimate the size of the link by looking at different properties, or different things. We can look at the changes in the cloud cover associated with the solar cycle, and then use satellite data to quantify how much are these changes in the cloud cover, or how large of a change in the energy budget will the changes in the cloud cover induce. But we can do something else. We can look at the oceans and use the oceans as a calorimeter to measure the effect of the sun. Basically, you look at how much heat goes into the ocean or leaves the ocean every solar cycle, and with that, quantify the effect that the sun has on the climate. We can also look at the 20th century, try to fit it, and then ask the question, for which parameters or which solar climate link do you, can you explain the 20th century? Okay, so you can use the cloud cover changes with measurements from the Earth Radiation Budget Experiment satellite, and you find that the change from solar minimum to solar maximum associated with the cloud cover corresponds to about 1 watt per square meter, which is a lot. It's comparable to what the CO2, the change in the energy budget associated with the anthropogenic forcing over the 20th century. Just for comparison, if you look at how large are the changes in the solar luminosity, the solar irradiance over the solar cycle, you find that between solar minimum and solar maximum, the changes averaged over the globe are 0.17 watts per square meter. So clearly, this effect is much larger than this effect. Now, when the IPCC modelers tell you that, oh, we take the sun into account, they're actually taking this thing into account. They're not taking this thing into account. Okay, how can you use the ocean as a calorimeter? You can use different data sets to see how much the oceans absorb or release heat. One of the nicest data sets is this one. You can use tide gauges to see by how much the seas are expanding or contracting. And it turns out that on short timescales, most of the expansion and contraction is because of thermal expansion and thermal contraction, not because of melting of ice. Now, if you look at the past 80 years, what you see is that the solar variations, which are in dashed red, okay, vary together with the rate of change of the sea level. Okay, so when the sun is more active, the oceans are expanding. When the sun is less active, the oceans are contracting. Of course, this graph has an average which is above 0, which implies that the oceans have been expanding over the 20th century. The sea level has been rising. But this has nothing to do with necessarily with the sun. Here you see that the oceans are expanding and contracting with the solar cycle, so you can quantify how much heat goes into the oceans with the solar cycle. Okay, this is actually the largest calorimeter in the world. It is the world. You can use other data sets and see the same thing, only there you have a problem with the completeness of the data sets and the different errors, but you can look at buoy data measuring the total amount of heat in the oceans. You can look at the surface temperature and then with the modeling get what the volume heat content is. And in any case, you always see that when the sun is more active, the oceans are expanding, and when the sun is less active, the oceans are shrinking. Okay, when I published this a few years ago, this was the data, the satellite data for the ocean sea level. Now, if this thing is indeed related to the sun, it means that with the newer published data, we should see the solar cycle in the satellite data. This is, mind you, the satellite minus the linear trend so that the average is constant. Do you see, with the newer data, the solar cycle? And the answer is that you do. Okay, very nicely. Okay, so since I published that paper, the oceans have learned what they're supposed to do, and are continuing to do that. Okay, how large are the changes in the heat content? If you look at the heat content changes, then you get, from the different data sets, you get variations which are somewhat more than 1 watt per square meter. If you ask the question, how large is the cloud forcing, and you add the solar irradiance to it, you see that it is consistent with what you see is going into the oceans. On the other hand, this is, for comparison, just the changes in the solar irradiance. Okay, so we know that the sun is affecting the climate. We have seen that it is very likely to be because of cosmic rays. And we know that the sun is affecting the climate to a large extent. We know how to quantify it. And we know that, that it's about 6 or 7 times larger than the changes in the irradiance. Now, what does it mean? What does it mean for the 20th century? Before that, let's try to empirically determine the climate sensitivity. We said that climate sensitivity is very important because we want it allows us to better understand what's going on in the 20th century, or it's important for the understanding of the 20th century, but it's also important for the understanding of the 21st century. We can empirically determine the climate sensitivity not by running global circulation models with very uncertain cloud cover recipes. We can look at historic or prehistoric or paleoclimatic variations in the energy budget, because we are looking at 2 different configurations of Earth, and ask what is the relation between the observed temperature change between those configurations and the changes in the energy budget between those 2 configurations, and empirically determine this relation, which is the climate sensitivity. We can play this game twice. We can do it once with the standard forcings, and we can do it again when we take into account the fact that the cosmic rays are affecting the climate. And we can do that for half a dozen different timescales. We can compare the temperature change to the changes in the CO2 over the Phaeronozoic, which is the last 500 million years. We can compare it to the cosmic ray flux. We can compare the mid-Cretaceous to today. 100 million years ago, it was much warmer on Earth. We can compare the Eocene to today. We can compare the last glacial maximum 20,000 years ago to the situation today. We can look at the warming over the 20th century, and we can look at oscillations over the 11-year solar cycle. This is one example. You can compare the temperature change that you see over the I wanted to say 11-year solar cycle, but that's not 11 years. That's 145 million years. That's our passages through the spiral arms of the galaxy. You can compare that to the cosmic ray flux, which is the graph I showed you before, and get one estimate for the sensitivity. And you can compare that to the CO2 and get another estimate. When you play this game for this half dozen different timescales, what you see is the graph on the left if you exclude the effects of cosmic rays. And if you do take into account the effects of cosmic rays, you get the graph on the right. Now, what do we see here? Here we see the sensitivity, or in terms of how much the temperature is supposed to increase if we double the amount of CO2. You see that each different time scale gives you a different sensitivity. But if you include the cosmic ray flux, if you take the cosmic ray flux into account, then lo and behold, all the different time scales give you a consistently the same climate sensitivity, which is roughly somewhere between 1 and 1.5 degrees for doubling the amount of CO2. Okay, okay. So we know that the cosmic ray flux also explain the climate more consistently, and they explain the climate more consistently with a lower climate sensitivity. Now let's see what it implies to the 20th century climate change. Over the 20th century, the interesting thing is that not only did the CO2, the amount of CO2 in the atmosphere increase, but also the solar activity increased. Now, if the sun has an effect on the climate, then this increase in solar activity should translate into an increase in the temperature. The question is now, what contribution comes from which source, or how large is the contribution of each of the sources? To answer this question, a student of mine built a one-dimensional climate model, which includes a lot of the different components, an ocean where the heat can diffuse into, a mixed layer, coupling between the oceans and land, the effect of the sun, the effect through an indirect effect of the sun on the climate. But the interesting thing is that what this student did, he left all the different unknown variables as free parameters. He said, let us suppose we don't know how large is the indirect effect that the sun has on the climate. Let's suppose we don't know what the climate sensitivity is. Let's suppose we don't know what the diffusion into the ocean is. Let's leave everything as a free parameter and ask the question, which model parameters give us observations which are consistent, give us predictions which are consistent with the observations. Then we can use some optimization algorithm, in this case it's a genetic algorithm, to optimize the parameters and then ask the question, what are the parameters that give you predictions which are consistent with the observations? And this is the result. What you see here, these are the predictions of the climate model. One of the graph is the predictions of the model, and the other graph is the observations, but I forget which one is which because they look quite the same. This is the residual, the difference between the two. And the difference between the two in the simple climate model is, in fact, twice better than the typical residual that you get when you fit the 20th century climate change with global circulation models. Now, you can ask the question, you can find you can get an estimate for what the probability distribution function is for the different variables by degrading the data and playing this game many times. And then you can get a probability distribution function for what the indirect solar forcing is, or what the climate sensitivity is, and so forth. What we find is that the indirect solar effect on the climate is around 1 watt per square meter, which, surprise, surprise, is what you find from the oceans or what you find from other mechanisms or other methods. So this method recovers the same quantification of the effect that the sun has on climate. But it also gives us a climate sensitivity which is close to that of a black body, namely one which doesn't have any feedback in terms of temperature increase for doubling the amount of CO2. It's this is 1.2 degree increase for doubling the amount of CO2. So it's about 1 degree increase per CO2 doubling. Okay, so this is the Ipcc range. Now, so I think I hope I managed to convince you that in addition to the anthropogenic forcing, we have another positive forcing, which is large, and that is that the effect that the sun has on climate. And it has this effect through modulation of the cosmic ray flux. In order to explain the 20th century, we necessarily get a low climate sensitivity. This low climate sensitivity is in fact consistent with a different empirical determinations of what the climate sensitivity is. But it's inconsistent with some of the GCM predictions that the climate sensitivity is very large. The low climate sensitivity, of course, tells us the increase over the 21st century is going to be small. How small? Well, we can use the same model to now integrate forward in time towards the 21st century, take a given emission scenario from the Ipcc, and then ask the question, by how much is the temperature going to increase? And when you do that and make many realizations, you find that the typical temperature increase is going to be around 1 and a little bit degree more than what has happened over the 20th century. How does that compare with the Ipcc predictions? This is how it compares with the Ipcc predictions. Is it good or is it bad? Is 1 degree a lot or not? I don't know. I'm not supposed to judge it. I'm just supposed to make the prediction. Okay, so let me summarize. There are very clear indications that the sun is affecting the climate, and it does so by modulating the cosmic ray flux, which affects the amount of atmospheric ionization. We have seen that there are different ways to quantify this link, and we find that the link is very large, namely 6 or 7 times larger than just variations in the total solar irradiance. And if anyone wants to build a consistent climate model, he has to take that into account, not just changes in the solar irradiance. What does it mean? It means that, okay, it's also consistent with the fact that the sensitivity has to be small. And if it's small, it means that only part of the 20th century warming is anthropogenic, maybe half, maybe a little bit more, maybe a little bit less. I cannot say for certain. But because the climate sensitivity is low, it's sitting below the Ipcc range, it means that the temperature increase over the 21st century is going to be on the low side, around 1 degree. And with this, I'll end.